When relocating an electrical panel that is fed from a transformer, several factors determine whether a disconnect is required between the transformer and the panel. The presence of a main breaker in the panel significantly influences this requirement. If the panel has a main breaker and the secondary feeders from the transformer are connected directly to this main breaker, then a separate disconnect between the transformer and the panel is generally not required. The overcurrent protection on the primary side of the transformer is designed to protect the transformer itself as well as the secondary feeders in the panel. This is based on the transformer's impedance and turns ratio, ensuring that any fault on the secondary side will cause the primary overcurrent device to trip, effectively disconnecting the transformer from the source. Article 240.21 V addresses the protection of transformer secondary conductors. Specifically, Article 240.21 V1 through 240.21. V5 outline different scenarios for protecting transformer secondary conductors based on their length and application. However, these sections primarily apply when the secondary conductors do not terminate in a main breaker protected panel. The exception for high bay lighting, as mentioned in Article 240.21 V4, is specifically for installations involving high bay lighting fixtures and does not typically apply to general panel installations. The primary overcurrent protection should be sized appropriately to protect the transformer. The National Electrical Code, or NEC, provides guidelines for sizing this overcurrent protection based on the transformer's kV amps rating and voltage. The general rule is that the primary overcurrent protection should not exceed a certain percentage of the transformer's rated primary current. For transformers rated over 600 volts, the overcurrent protection is typically set at 125% of the transformer's primary current. For transformers rated 600 volts or less, the overcurrent protection is generally set at 250% for transformers with impedance not more than 6%, and 125% for transformers with impedance more than 6%. When selecting the appropriate overcurrent protection, it is also crucial to consider the transformer's inrush current, which is the high initial current that flows when the transformer is energized. The overcurrent protection device should be able to withstand this inrush current without tripping. This is typically achieved by using time delay fuses or inverse time circuit breakers. The ampacity of the secondary conductors must also be considered. The secondary conductors should be sized to carry the calculated load served by the panel, and their ampacity must be at least equal to the overcurrent protection device protecting them. The NEC provides tables, such as Table 310.16, that specify the ampacity of conductors based on their size, insulation type, and ambient temperature. It is important to select conductors with the appropriate ampacity to ensure safe and reliable operation. The length of the secondary conductors is also a factor to consider. While the NEC provides specific rules for conductor protection based on length in certain situations, these rules typically apply when the secondary conductors do not terminate in a main breaker protected panel. However, it is still important to minimize the length of the secondary conductors to reduce voltage drop and improve system performance. Voltage drop can be calculated using Ohm's law and is affected by the conductor's length, current, and resistance. Excessive voltage drop can cause equipment to malfunction and can also lead to increased energy consumption. Therefore, it is important to select conductors with a large enough size to minimize voltage drop, especially for longer conductor runs. Grounding is another critical aspect of transformer installations. The transformer's secondary winding must be grounded in accordance with the NEC. The grounding system should be designed to provide a low impedance path for fault current to return to the source, which helps to ensure that overcurrent protection devices will trip quickly in the event of a ground fault. The grounding electrode conductor, which connects the transformer's secondary winding to the grounding electrode system, must be sized appropriately based on the size of the secondary conductors. The grounding electrode system itself should consist of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes. Bonding is also essential for ensuring electrical safety. All metal enclosures, such as the transformer enclosure, panel enclosure, and conduit, must be bonded together to create a continuous electrical path. Bonding helps to equalize the voltage potential between different metal parts, which reduces the risk of electric shock. The bonding jumpers used to connect the metal enclosures should be sized appropriately based on the size of the circuit conductors. In addition to the NEC, local codes and regulations may also apply to transformer installations. It is important to consult with the local electrical inspector to ensure that the installation complies with all applicable requirements. The inspector can provide guidance on specific issues and can also help to ensure that the installation is safe and reliable. When relocating an electrical panel, it is also important to consider the available working space around the panel. The NEC requires that there be sufficient working space in front of the panel to allow for safe operation and maintenance. The working space should be clear of obstructions and should provide adequate headroom. The depth of the working space depends on the voltage of the system and the presence of exposed live parts on the opposite side of the working space. The NEC also requires that the panel be properly labeled to identify the circuits that it serves. The label should be clear and legible and should accurately describe the purpose of each circuit. This helps to prevent confusion and makes it easier to locate and identify circuits during maintenance and troubleshooting. Furthermore, the panel should be installed in a location that is readily accessible and protected from physical damage. The panel should not be installed in damp or wet locations unless it is specifically designed for such environments. The panel should also be protected from impact and other physical hazards. When working with electrical equipment, it is essential to follow safe work practices. Always to energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Never work on live electrical equipment unless it is absolutely necessary, and always follow lockout-tagout procedures to prevent accidental energization. Lockout-tagout involves disconnecting the power source and applying a lock and tag to the disconnect switch to prevent it from being turned on. Only authorized personnel should be allowed to remove the lock and tag. Regular maintenance is also essential for ensuring the safe and reliable operation of electrical systems. Transformers should be inspected periodically for signs of damage, such as oil leaks, corrosion, or overheating. The connection should be checked for tightness, and the overcurrent protection devices should be tested to ensure that they are functioning properly. Panels should also be inspected for signs of damage, such as corrosion, loose connections, or damaged components. The breakers should be tested to ensure that they trip properly, and the panel should be cleaned to remove any dust or debris. By following these guidelines, you can ensure that your transformer and panel installation is safe, reliable, and compliant with all applicable codes and regulations. In summary, if the panel being relocated has a main breaker and the secondary feeders from the transformer land directly onto the main breaker, a separate disconnect between the transformer and the panel is not typically required. The primary overcurrent protection adequately protects the secondary side, given it is appropriately sized. The specific exception for high bay lighting in Article 240.21 B4 does not generally apply to standard panel installations. Always consult the latest edition of the NEC and local codes for the most accurate and up-to-date information. Remember that electrical work should always be performed by qualified and licensed electricians to ensure safety and compliance. The proper sizing of the primary overcurrent protection is crucial. The overcurrent device must protect the transformer from overloads and short circuits. The selection depends on the transformer's voltage and impedance. For transformers over 600 volts, the overcurrent protection is usually set at a maximum of 125% of the transformer's primary current. For transformers at 600 volts or below, different rules apply based on the transformer's impedance. If the impedance is not more than 6%, the overcurrent protection can be up to 250% of the primary current. If the impedance is greater than 6%, the limit is 125%. It is important to understand transformer inrush current. When a transformer is energized, it draws a high inrush current. The overcurrent protection device needs to be able to handle this inrush without tripping unnecessarily. Time delay fuses or inverse time circuit breakers are often used to accommodate inrush current. Conductor ampacity is another critical consideration. The secondary conductors must be sized to carry the load served by the panel. The ampacity of the conductors must be at least equal to the rating of the overcurrent protection device. NEC Table 310.16 provides ampacity ratings based on conductor size, insulation type, and ambient temperature. Selecting the correct conductor size ensures safe and reliable operation. Voltage drop is also important, especially for longer conductor runs. Excessive voltage drop can cause equipment to malfunction and reduce efficiency. The length of the secondary conductors should be minimized to reduce voltage drop. Calculations using Ohm's law can help determine the appropriate conductor size to minimize voltage drop. Grounding is essential for safety. The transformer secondary winding must be properly grounded according to the NEC. The grounding system provides a low impedance path for fault current, ensuring that overcurrent devices trip quickly in the event of a ground fault. The grounding electrode conductor must be sized correctly based on the size of the secondary conductors. Bonding is also necessary to equalize voltage potential between metal enclosures. All metal enclosures, such as the transformer enclosure and the panel enclosure, must be bonded together. Bonding jumper should be sized appropriately based on the circuit conductors. Local codes and regulations must also be considered. These codes may have additional requirements beyond the NEC. Always consult with local electrical inspectors to ensure compliance. Working space around the electrical panel is important for safety. The NEC specifies minimum working space requirements in front of electrical panels. This space must be clear of obstructions and provide adequate headroom. Panel labeling is also crucial. All circuits in the panel should be clearly labeled to identify their purpose. This helps with troubleshooting and maintenance. The panel should be located in an accessible and protected location. It should be protected from physical damage and not installed in damp or wet locations unless specifically designed for such environments. Safe work practices are essential when working with electrical equipment. Always to energize circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow lockout-tagout procedures to prevent accidental energization. Regular maintenance is important for the safe and reliable operation of electrical systems. Transformers should be inspected for damage such as oil leaks or overheating. Connections should be checked for tightness. Overcurrent protection devices should be tested regularly. Panels should be inspected for corrosion, loose connections, and damaged components. Breakers should be tested to ensure they trip properly. The PAL should be cleaned to remove dust and debris. These maintenance practices help ensure the longevity and safety of the electrical system. Always adhere to the latest edition of the NEC and local codes for the most accurate and up-to-date information. Consult with qualified and licensed electricians for any electrical work. Electrical safety is paramount, and proper installation and maintenance are crucial for preventing accidents and ensuring reliable operation. It is essential to adhere to all safety guidelines and regulations to protect both personnel and equipment. The primary side protection is a crucial part of the entire system. The primary overcurrent protection must be properly coordinated with the transformer's characteristics. The protection device should be sized to protect the transformer against overload and fault conditions. The primary protection also provides backup protection for the secondary side. In case of a fault on the secondary side, the primary overcurrent device should trip, isolating the transformer from the source. The primary protection device must be able to interrupt the available fault current. This is the maximum current that can flow during a fault condition. The available fault current depends on the impedance of the source and the impedance of the transformer. The interrupting rating of the overcurrent device must be greater than the available fault current. Coordination studies are often performed to ensure that the overcurrent devices are properly coordinated. A coordination study is an engineering analysis that determines the optimal settings for overcurrent devices. The goal is to minimize the extent of an outage during a fault condition. The coordination study ensures that the overcurrent device closest to the fault trips first, while upstream devices provide backup protection. Transformer impedance plays a significant role in determining the fault current. The impedance of the transformer limits the amount of current that can flow during a fault condition. A higher impedance results in a lower fault current, while a lower impedance results in a higher fault current. The transformer impedance is typically expressed as a percentage of the transformer's kV/amps rating. The transformer's nameplate provides important information about the transformer. The nameplate includes the kV/amps rating, voltage ratings, impedance, and other critical parameters. The information on the nameplate is essential for selecting the proper overcurrent protection and conductors. Transformer loading is also important. The transformer should not be overloaded. Overloading can cause the transformer to overheat and fail. The transformer's load should be monitored to ensure that it does not exceed the transformer's kV/amps rating. Power quality can also affect transformer performance. Harmonics, voltage sags, and voltage swells can all impact the transformer. Harmonics are caused by nonlinear loads, such as electronic equipment. Voltage sags are temporary reductions in voltage, while voltage swells are temporary increases in voltage. These power quality disturbances can cause the transformer to overheat, vibrate, and fail. Power quality monitoring can help identify and mitigate these issues. The use of filters and surge suppressors can improve power quality and protect the transformer. Transformer maintenance is an ongoing process. Regular inspections, testing, and cleaning can help extend the life of the transformer. A visual inspection can identify potential problems, such as oil leaks, corrosion, and loose connections. Insulation resistance testing can assess the condition of the transformer's insulation. Turns ratio testing can verify the transformer's turns ratio. Infrared scanning can detect hotspots caused by overheating. Oil sampling can assess the condition of the transformer's oil. These maintenance practices help ensure the safe and reliable operation of the transformer. Remember that electrical work should be performed by qualified and licensed electricians. Safety is always the top priority. The NEC and local codes provide detailed requirements for electrical installations. Adhering to these requirements ensures a safe and reliable electrical system.